Today, we're going to take another look at the fundamental theorem of calculus. And this falls in the category of, but wait, there's more. Because at this point, I'd only given you half of the fundamental theorem of calculus. If I'm following the book's plan, I got to wait a whole other chapter to get you into the second half of the fundamental theorem of calculus. And that seems a little deceptive to me. So we're just going to go on to the second part right away. Here are the pieces that we need for this to work. We need a continuous function on a closed interval, and we need just some value from that closed interval. Any value at all. Anything will do. And I keep saying closed interval because A and B need to be included, but especially for the second part, we can use the entire number line, which is not a closed interval. So if f is continuous anywhere, if f is continuous everywhere, that is for all real numbers, then it is certainly continuous on any closed interval. So that only makes things stronger and easier to attain. So C is any value on that closed interval. The first part of the fundamental theorem is familiar to us. The definite integral from a to b of f prime of x to x is f at b minus f at a. The definite integral of a rate of change on an interval is the amount of change on that interval. I phrased this a little bit differently because I dropped the f prime in the integral part. And so I'm trying to emphasize the relationship that f is an antiderivative of f prime, and f prime is the derivative of f. Trying to emphasize the relationship between the derivative relationship and the antiderivative relationship. So one of the things that we're getting from the fundamental theorem is that this antiderivative idea is aptly named. This integration is almost the inverse of differentiation. Now let's get to the second part. The second part says this function capital F of x defined to be the definite integral of from c to x of f of t dt is an antiderivative of little f. Let's see why this matters. In the first part of the fundamental theorem of calculus, we are evaluating a definite integral using the antiderivative. So we want to evaluate a definite integral, so we look at the antiderivative and use that. In the second part, we're going the other direction. We are constructing an antiderivative using the definite integral. So in the second part, we want an antiderivative, and so we use the definite integral. So this works, this fundamental theorem of calculus business works both ways. We're emphasizing that integration is almost the inverse of differentiation. And we're connecting this definite integral business to the antiderivative business. So in the first part, we're using the antiderivative to evaluate a definite integral. In the second part, we're constructing an antiderivative using the definite integral. So let's take a look at an example. So if we want to evaluate the definite integral from, let's say, 1 to 4 of the square root of x dx. In this, when I write this definite integral down, we want to evaluate this definite integral. So we're going to use the antiderivative to evaluate the definite integral. Here, we will use the antiderivative to evaluate the definite integral. So we find the antiderivative. We read the square root of x as an x to the 1/2 power. So the antiderivative will add 1 to the exponents and divide by the new exponents. And then yesterday we mentioned the plus some constant. But we just need an antiderivative of x to the 1/2 power. So I'll use the one where the constant is equal to 0. So we find an antiderivative of a square root of x, 2/3 x to the 3/2, and evaluate from 1 to 4. Here's the antiderivative that we're using to evaluate the definite integral. So this means we find f at b and subtract f at a. So 2/3 times 4 to the 3/2 minus 2/3 times 1 to the 3/2. Four to the 3/2 is the square root of 4 cubed, or the square root of 4 cubed. So 4 to the 3/2 is the square root of 4 cubed, or the square root of 4 cubed. So the square root of 64 is 4. Sorry, the square root of 64 is 8. I was looking at all the 4s. The square root of 64 is 8, or 2 cubed is 8. In either case, we get 8. So I got 2/3 of 8. One to the 3/2 power is just 1. So I got 16/3 minus 2/3, 14/3. In this case, we use the antiderivative to evaluate the definite integral. Any questions? The second part is useful in constructing antiderivatives when we can't do our little add 1 to the exponent and divide by the new exponent. So the second part, I can say, well, capital F at x, defined as the integral from 0 to t of e to the minus t squared dt. Oops, not the integral from 0 to t, the integral from 0 to x. Is an antiderivative of f of x equals e to the minus x squared. That is, if f of x is the integral from 0 to x of e to the minus t squared dt, then f prime is e to the x squared. Minus x squared. It's important to be able to do this because e to the minus t squared does not have a nice antiderivative. So the reason that we would want to do such a crazy thing So we need to construct the antiderivative of e to the minus x squared. So we need to construct the antiderivative of e to the minus x squared because e to the minus x squared does not have what I call nice antiderivative. And when I say nice antiderivative, that I mean finite combination of elementary functions. And now you can see why I say nice. So when I say nice antiderivative, I mean a finite combination of elementary functions. There are two elements there. Finite combination of elementary functions. One, finite combination. Two, elementary functions. So if I want a finite combination for my antiderivative, I can't use elementary functions. So I construct it using the definite integral. Or if I want to use elementary functions, I'm going to need to use an infinite combination of them. We haven't gotten to that part yet. Now, this is super useful because definite integrals are easy to approximate to any degree of accuracy. So we do this because we can easily approximate a definite integral using area. And we can do this especially with the amount of computing power to any degree of accuracy we happen to need. Even with a very small amount of computing power, we can approximate definite integrals to 12 decimal places. That is a lot. So we can now approximate the value of this antiderivative function to any degree of accuracy. And that's why this construction portion is important. Now we can evaluate the antiderivative just using area. If I need to know what f of 1 is, I'll just do math 9 and f an integral of e to the minus x squared, e to the minus x squared, with respect to x from 0 to 1. If I need to evaluate the function at 2, I just integrate from 0 to 2. If I need to evaluate the function at 3, I can plug in negatives if I want. Shouldn't be surprised by that. E to the minus x squared is an even function. Any questions?
Professor,
shoot, I did minus x squared. It's an odd function.
Professor Lich,
Yes.
you don't mind if I ask? On the first example, we have the integral 1 to 4, the square root of x. So we can take the antiderivative, and then we can set to like a big F B minus big F A.
Yes.
And then on the second one, we have to construct the antiderivative. So if we have to go to x, all we need to do just plug the x into the e negative t square. All we need to do just plug that whatever value.
No, we're not plugging x into the e to the minus t squared. We're doing the definite integral from 0 to whatever we want to plug in. So if we want to figure out f of, let's say, 1, the 1 doesn't go into the e to the x squared. We integrate from 0 to 1. That's where the 1 goes. It goes in the endpoint of the definite integral. We integrate from 0 to 1 the function e to the minus t squared dt.
And the endpoint is 1, am I correct?
Yeah.
Okay. But
So,
on the example, the endpoint is the x. That's why we have the x in there, correct?
yeah. That's why I put the x there. So then we evaluate that on our machines and we get 0.747.
On the second example, we don't have to take any derivative. All we need to plug in the endpoint.
We're plugging in the endpoints, but we're plugging into the definite integral, not into e to the minus x squared. We're not plugging into e to the minus x squared. We're plugging into the definite integral.
Are they the same answer, like the area? No.
The derivative and the function are not the same.
All right, thanks for the explanation.
I think I made a verbal correction that I didn't actually verbally correct. I said the same thing incorrectly in a different way. E to the minus x squared is an even function. Its antiderivative happens to be an odd function. That's why we got the opposite sign when we integrated from 0 to -1. So e to the minus x squared is an even function. The antiderivative of e to the minus x squared is an odd function. When we start at 0. All right. So what you want to remember, first of all, is that there are two parts to the fundamental theorem of calculus. It should seem important. The class is called calculus, and this is the fundamental theorem of it. So we should know that there are two parts to the fundamental theorem of calculus. You should be able to write them down with their symbols. Definite integral from a to b of f prime of x dx is f at b minus f at a. And capital F of x, defined to be the definite integral from 0 to x of f of t dt, is an antiderivative of f of x. More importantly, you should understand that in the first part of the fundamental theorem of calculus, we are evaluating a definite integral using an antiderivative. And in the second part of the fundamental theorem of calculus, we are constructing an antiderivative using the definite integral. Any questions? Now, this becomes very dangerous knowledge because eventually I'm going to ask you for a bunch of antiderivatives. And I'll say something like, find the antiderivative of the function. And then I'll give you a function, say f of x is square root of x. And what I'm intending that you do is say, I'm going to read this as x to the 1/2 power. So the antiderivative is 2/3 x to the 3/2 and then plus c. Because the derivative of 2/3 x to the 3/2 is x to the 1/2. And then I'll say something like g of x is cosine x. And my intention for you would be for you to write the function whose derivative is cosine x. And the derivative of sine is cosine. So I intend for you to write sine x plus c. And I take off 1,000,000,000 points if you leave off the plus c. That's actually the true origin story of Billy Madison. He was in calculus class, everything was going fine until he left off a plus c, lost 1,000,000,000 points, and found himself back in whatever grade he was in that movie. I only know what that movie is like in the broad strokes. I haven't seen it yet. I shouldn't say yet. I don't know if I intend to see it. But if you want to be sneaky, and it's like, ugh, I don't want to do this add one of the exponent and divide by the exponent business. If I just said write an antiderivative of the given function, if you wrote that, you'd be like, oh, technically that is an antiderivative. But then you would be stuck with the technically clause. If you're in an argument and you have to say, well, actually, you're probably losing, and you really need to evaluate your priorities. Because I would just counter with the, you know what I meant. We're not in a court of law, which is called the Judge Dredd rebuttal. But, you know, technically, so technically those are antiderivatives of root of x and cosine of x, respectively. But then if I'm asking you, if we just talked about how to find antiderivatives, and I asked you to find some antiderivatives, you know what I meant. Any questions?
Yes, for first image, could you give us the notation of the first example? We have like f of x equal to square root of x. On the
So the notation that I used before, this would have been the capital F.
And the one on the left would be?
This is also capital F. Both of these are antiderivatives.
You mean like, so on the right will be the capital F, and on the left, f of x will be, oh, okay.
Yeah, here's the derivative of this function. So this would be the capital F. The reason I didn't write the capital F of x notation, the reason I didn't write the capital F is not actually standard notation. It's a local notation that this book happens to use, where the capital is the antiderivative of the lowercase one. So we could say that this is the g of x, but that's not a universal notation by any means. So, but what I'm saying is that these ones in red, those are constructions of antiderivatives using the second fundamental theorem of calculus. And in the first one, we're actually using rules. So if I had a third function here, and I'm just going to use the same one that we had, e to the minus x squared. Well, if we go to find capital H of x, we would have to construct the antiderivative. Because of the function e to the minus x squared does not have a nice antiderivative, there is not a nice antiderivative. I can't just write a nice, simple, closed, a nice finite combination of elementary functions. I have to use this finite combination of non-elementary functions. Any questions?
Professor Lee, so on the three example, the first two is the evaluate one, am I right? And the last one, h of x, is the construction, am I right? No.
No, we're not evaluating definite integrals here. I'm just saying find an antiderivative of the given function. The first two, we have nice antiderivatives. We can follow the rules. We add one to the exponent. We divide by the new exponent. On the second one, we just know that cosine of x is the derivative of sine of x. But on the last one, there is no nice antiderivative. We have to construct the antiderivative using the second fundamental theorem. That's all I'm saying. There are some functions out there that don't have nice antiderivatives. This is a big change from what we encountered when we were finding derivatives. Now that you're armed with the product rule, quotient rule, and chain rule, there's not a function that I can construct that's differentiable that you can't just use some combination of those rules to find the derivative of that function. But when we start going the other way, I can't just give you any function and ask you to find an antiderivative using some small set of rules. Because some functions, like e to the minus x squared, don't have nice antiderivatives. And I think I've mentioned it before, but e to the minus x squared is a really important function for us. And one of the things that we want to know about this function is the area under the curve, because it represents a normal distribution. So it'd be really handy for us if we had an antiderivative for that, but we don't. We have to approximate it by constructing an antiderivative using the second fundamental theorem of calculus and coming up with values through approximation. Math is weird sometimes. All right, that's our big news for today. That's our big finish for the week. The second part of the fundamental theorem of calculus, which allows for the construction of antiderivatives and the relationship between the two. We can use antiderivatives to evaluate a definite integral. We can use the definite integral to construct an antiderivative. That's the complete fundamental theorem of calculus, at least until we get to functions of more than one variable and vector-valued functions. All right, that's going to do it for today. That's going to do it for this week. Everybody have a good weekend. I'll see y'all on Monday. Thanks for playing.